Can you hear me?
Yes, we can hear you.
Okay. I'll start in 1 minute the session.
Hi, Benjamin. Did you see my private chat?
No. Just wait a second. Yes. That's fine. Okay, so it is 2 p.m. Time to start this new circle session, which will deal with indexation and annotation. So the first talk will be given by Nathalie Neptune, and it has to do with Earth observation imagery and annotation. So Nathalie, you have 15 minutes plus 5 minutes for questions. You have to unmute your mic, Nathalie. Okay, go ahead.
Okay, good afternoon, everyone. My name is Nathalie Neptune. I am a PhD student, and I work under the supervision of Professor Josiane Mott. And I'm going to present our proposed approach for automatic annotation of change in Earth observation imagery. To put the work in context, we are working on change detection in Earth observation data. And Earth observation images, the ones we're mentioning, are essentially from satellite missions, such as the Landsat or Sentinel programs. And we are working on detecting changes in such images. The basic principle of change detection is to compare two images in a given area at different times, and then to find out if something has changed within that time frame. And you can see in the illustration on the side, two images. I'm sorry?
See your slides.
You don't see the slides?
No, just you.
Oh. Wait, what happened? This is weird. What should I do? Let me try this.
You have to share. Yeah.
Huh. Does this work?
Yes, it does.
Okay, great. So yeah, I was talking about the example that you can see of two images taken at two different times with 6 days between them. And between that time, there are some patches that appear in that area. And those are the type of changes that we are looking to detect. And we are also doing semantic annotation of those changes. And in the illustration, you can see patches, and here we label them as deforestation. So why is it interesting to annotate those changes? Is because most of the data that is available for Earth observation is not annotated. It's unlabeled, and therefore there's a need to add those annotations. And when we talk about semantic annotations, we are talking about semantic descriptors that are added to the changes that are detected in those images. And there are different ways to do this. One way that it can be done is by comparing the classes that are present on the images, such as, for instance, saying that the patch went from forest to agricultural area, or from forest to bare soil. So this way we mention the transition that happened, or we could use a simple descriptor like deforestation to characterize the change. So we are proposing to use scientific literature as a source of the annotations. Annotating Earth observation images is costly because it requires experts to do the work. And when you're working with satellite images, you might be working in very large areas. Let's say you are working on the Amazon, for instance, you could be dealing with areas of maybe hundreds of thousands of square kilometers at once. And therefore, there is a need for automatic or at least semi-automatic methods to provide those annotations. Also, we know that within earth sciences, publications are plentiful. In fact, across all areas of science, there has been exponential growth in the number of publications over the last few decades. We are proposing to use visual semantic embeddings for annotating the changes. And basically, it's about representing the visual and the textual data in the same latent space. And within that space, the representations of the data that are close are also close semantically. And we are proposing to apply this to the case of deforestation detection, which is the loss in first cover in images of forested areas. There are several related works to what we are proposing. There are work that are done on binary change detection. And when we say binary change detection, we mean the detection of the presence of change in the images, but without providing any semantic labels. And essentially, this is typically done using image segmentation models. And recently, there has been deep learning models that have been proposed to do this. Lately, there's been models based on UNet that have been proposed, and previously there had been models based on VGG as well. And to learn the semantic labels, there are traditional methods such as post-classification, which is the comparison of the classes present in the images, which has several drawbacks, and one being that you're accumulating the errors of the different classifications because the images are classified separately. But there are also, of course, the direct learning of the change labels. If you have label changes in your data set that you can learn from, you can directly learn those changes. But this requires that you already have changes that are already labeled. And in the absence of such labels, there are methods that have been proposed using ontologies or georeferenced Wikipedia articles to do this task. And finally, from computer vision, there are methods based on zero and few-shot learning that have been proposed for land cover classification tasks. So the research questions that we want to address are the following. How can we combine image change detection with text information extraction in order to perform semantic change detection? And basically what we are looking for is to add the semantic annotations to the changes that we are detecting in the images. And we also ask this other secondary question, which is how can we improve the performance of the change detection in the images by using the annotations that we can extract from the text when we are training the visual model. And in order to make our proposal, we made a few hypotheses. And one of them is that the relevant annotations that we can extract from the existing publications and use for the semantic change detections in the absence of labels provided by the expert are present in their publications. In other words, what we're saying is that the scientists have studied the changes that are occurring, and they have documented their findings in their publications, and those publications are available, and we can extract relevant annotations from them. And also, we are saying that we can use the visual semantic model to make the link between the changed segments and the labels that we are able to extract from the text. Another hypothesis that we're making is that if we, or when we are using the annotation in the training as privileged information, we will have the change detection model that will perform better than when we use it only with the image data. So to test this approach, we are using data from a test site in Peru. It's in Madre de Dios, and you can see on the right the location of the area in South America. And data set is made of radar imagery from Sentinel-1 and also optical imagery from Sentinel-2. And we also have alerts, which is data from a forest loss alert system called GLAD, and that is provided on a daily basis. And we have data from another system called GeoBosques that is provided on a yearly basis. And you can see samples of the radar, the optical, and the alerts data on the right. We also have data from publications that were extracted from the Web of Science. It's made of abstracts that are related to this area that were published from 2000 to 2019. And for the satellite images, we are working in collaboration.
Sorry to interrupt again. The presentation just disappeared.
Again. Yes. Sorry, I don't know what happened.
I don't know.
I have to reshare at each time. I don't know what to do. Is it back?
Yes, it is.
Okay.
Go ahead.
Sorry. Okay. I can see it here. So, yeah, we are working with remote sensing scientists who are working with data from this area, and that's how we have part of the data. Okay, so our method is about combining image segmentation and the annotation of the segments to perform the semantic annotation of the change detection in satellite images. And to do the segmentation part, we propose to base our approach on state-of-the-art methods that already exist, that use deep learning, and that were proposed by Dot and Peng. And for the annotation, we want to use with embeddings that were pre-trained on Wikipedia, but are aligned with our text data using the RCSLS criterion, which was proposed by Brzezinski. So essentially what we want to do is use visual semantic embeddings. So the joint embedding of image and the words that we project in the same space, as was proposed by Fromm. So the idea is to match the representation of the images and the text vectors. And we can do that if we have a set of known classes. And we also want to do to use the learning using privileged information paradigm, which was first proposed by Vatnik, with deep learning implementation proposed by Lambert. With that, it's just the idea of after extracting the labels, we can use them as privileged information when we are training the visual model. And in the side, you can see essentially the idea of taking image pairs, using the visual semantic model to have labels and add them to a binary change detection map, and this way label the changes. So in conclusion, we are proposing to use expert knowledge gathered from text in an unsupervised way to add semantic information to changes detected in images as a method for identifying change in satellite images in an area of interest using open data in cases where expert annotations are not available. So we propose to improve on image change detection accuracy by using the text data as reversion information. And we are proposing to apply this approach to the case of detecting loss in forests, but applications into other domains are also possible. And as an extension of this, we are thinking about adding event extraction from the text of the publications. And in this way, in addition to detecting the changes, we can also track them jointly with the text and the images. So this is just a snapshot of the references. I thank you for your attention. And if you have any questions, please feel free to just ask them. Thank you.
Okay, thank you, Natalie. We have a few minutes for questions. So I don't know if there is somebody wanting to ask a question. So, well, I guess it's preliminary work, and because you didn't present any results. So,
yes.
But before discussing a bit this, so you use an ontology to define the different classes.
I'm sorry? I didn't quite get it.
Yeah, just to clarify a bit the things. You said that you use an ontology to define the classes. No. Okay.
No, no, sorry. No, I said there is work where they use ontologies, but in our cases, we're not. No.
Okay, so I didn't get this point on how do you define the classes you.
Okay, so the idea is. Yes, sorry. So the idea is to go. We're working with a known problem, which is the problem of forest loss. So in this application case, we know, I'll say, the main change class. And from there, we can learn this class, but also related classes by using the word embeddings and by taking vectors that are close to our known class. I don't know if it's clear or not.
Not completely. So you have just one class, which is the forest loss.
Yes, yes.
And you have a set of publication. And what is not clear is how do you match both? That's maybe I
how do I match what?
The images with the forest loss. How do you know there is a forest loss or not?
Okay, so from the text, I can already extract the important keywords. Keep in mind that I have a set of texts that are related to what I'm looking for, and that they do include those keywords, and they do include exactly the keyword of, well, the deforestation or exact similar keywords, right? So this I can match, but the idea is to match, to expand it to related keywords, but I already have like specific matches for deforestation.
Okay, so you use word embedding basically to match different texts that don't mention the keywords with those. Okay.
Yes.
And so do you have any plans on how to extend this? Because I guess that the global intent is to have classes defined automatically in a way and to be able to classify whatever image and to use the text of the scientific publication.
In case where we don't know, I guess For now, I can see it working in case where you have at least some idea of a minimal number of classes, like really a very small number of known classes. And when you apply that model, you can discover unknown classes, but you do have to start at this point, I guess, for now, with at least something that you know, even though you can discover some things, other classes that you don't know from there. But starting from completely zero, like in a case where you want to learn classes that you have absolutely no ideas about, I guess this is not yet, for this proposal, it's not yet there.
And just could you go back to the slides where you mentioned the projection of images and text on in the same space using the
Which one? Which
one?
one? This one?
Yeah, this one. So what you do in this case
Yes.
is basically to project the images on the text, and you try to match the text of the publication or the abstract with the image.
Yes and no. So,
oh, okay.
Yes, I mean, yes, not totally, because we're really working on a per word basis, not the whole text. So it's on a per word basis. And what we try to do is have the model learn to learn how can I say this? Learn when the image is similar to its label. So it's a combination. So in the original proposed method, it's a combination of cosine similarity and rank loss. So it's an image is close to its label in the space. So you want the model to learn that. And at the same time, you want it to learn that it's farther from the labels that are not its own label. And you can do that since they are now in the same vector space.
Okay. Okay. So I guess it's time to go to the next paper. Thanks for your presentation. And
thank you so much.
And okay, so I don't know if the next presenter is ready. Is Nieves, Ana?
Yeah, give me 1 second.
No, it's Guillermo. Okay.
Yes, I'm here.
Okay, so Guillermo de Bernardo will present the improved compressed string dictionaries, which is a joint work between Coruña University and the University of Chile. Okay, can you go ahead, Guillermo?
Thank you. I hope you all can see everything all right.
Yeah, that's fine.
This paper, as the title says, tackles the problem of the compressed representation of string dictionaries. We focus on space efficiency. So I'll start by defining our understanding of a string dictionary and what are the kind of operations that we aim at solving. We consider the string dictionary is a mapping between strings and identifiers that will usually be consecutive integers. Particularly, we also consider that the set of strings that we're storing does not have an explicit order, so we can sort them lexicographically. We assume that we can do that, and we assume that these IDs can be assigned in this lexicographical order. We focus on two application areas where this is usually the case. Two well-known areas such as web graphs and RDF datasets. They share the same idea of a representation that can be seen as a graph where nodes are labeled with a specific string, which in web graphs would be URLs, and edges would be links between URLs. So using a string dictionary, we just transform this graph into a graph where nodes are labeled with numbers, and we have a separate structure that maps between those numbers, those integers, and the corresponding strings. The idea here is that first, the strings are usually much larger and more difficult to compress than the structure of the graph itself. So by separating this, we can solve the two problems separately. And also, we can solve many basic operations on the web graphs, for instance, with simple queries on the string dictionary combined with more complex queries on the structural graph. For instance, if we want to find all the URLs that are a successor of a given one, that is, that are pointed by a given one, we first look up the string in our dictionary to get the corresponding ID. Then we run in any representation structural part of the web graph. And then for each result that we obtain, that is an identifier, we map this ID back to a string using access operations in our dictionary. So essentially having only these two very basic operations that map between string to ID and vice versa, we can delegate many basic operations to the structural part of the graph and only need these two basic techniques in the dictionary part. So for the representation of a string dictionary, we can use a wide number of solutions. Basic data structures such as hash tables and tries can be used, but we focus on the compressed version. Of course, there have been solutions proposed that are based directly on compressed versions of hash tables and tries, usually combined with some ideas mainly coming from text conversion, since the length of the strings in web graphs and RDF datasets, since they are URLs and that kind of strings, can usually be exploited to improve compression, taking advantage of regularities in those strings. There are two solutions that share some similarities with our work. They have been published more or less recently. The first one is called differential encoding dictionaries, and it's essentially based on from coding to remove regularity at the beginning of the strings. In the case of URLs, we have many common prefixes between the strings in our collection. The other solution is RDAC, is based on a compression technique called repair that is used to compress the full sequence of strings and is combined with a kind of binary search algorithm to locate the appropriate string in this collection. Our idea essentially combines ideas from both of these and uses some ingenious algorithms to improve their performance. So we assume that we have a set of strings that are sorted in lexicographical order. I add a terminator to each of them, but this string marker can later be removed. And then we also set two marker strings that share no prefix in common with any string in our collection at the beginning and at the end. And we store two arrays, LCP and RLCP, that will be one of the two main parts of our structure. We set the values in those two arrays to 0 for the beginning and end, and then we do a kind of binary decomposition of the array to fill all the positions. At the midpoint, for instance, we set in LLCP the longest common prefix between the string at position 8 and the string at the beginning, which is a marker, so at this midpoint, it will be 0. In RLCP, we do the same, but we store the longest common prefix with the rightmost position in the array. And then we recurse on each half. For instance, at position 4, our LLCP is again 0 because the string at position 0 is a marker. It has no common prefix with the string at position 4. But our LCP is 1 because ceiling at position 4 shares the first character in common with clamp, the string at position 8. And we essentially do this recursively in all the fragments of the array until we have LLCP and RLCP built. And then we use these LLCP arrays to remove the corresponding prefixes of each string. Of course, we expect that in web graphs, for instance, these prefixes will be relatively long. For each position, essentially the maximum of the values in both, and we remove the prefix of that. For instance, for position 1, we remove the first two characters, And we do that for every other position in our collection. And this is essentially the information that we want to store, the true arrays plus the string tails, the non-grayed out part in each string that remains after this prefix removal. Using this, we can easily look up a word following a kind of adjusted binary search combined with our specific arrays. We set two variables L and R that represent the longest common prefix between the query string and the leftmost and rightmost position in our search so far. So initially they are set to 0 because we have the marker strings at the beginning and at the end, which are just dummies. And then we start searching at the midpoints. At the midpoint, we always need to search because both values in our LCP arrays are 0. So we need to compare the string at position 8 with our query string. In this case, we would have to compare this string clamp with the query string that's clamp. And our comparison tells us that they share 4 characters in common and that the query string clamp is to the left, that is lower lexicographically than the string at position 8. So we can recurse on the left half of the array, and we set our R, the longest common prefix of the rightmost string, to 4. The key idea is that at this second step, we check the RLCP, because R is the higher value between L and R, and we compare it with our value of R. In this case, RLCP at position 4 is 1, which is lower than R. This means that the string at position 4 has 1 character in common with the string at position 8, which is less than the similarity between the string at position 8 and the query string. So we immediately know that we have to go to the right half of this interval without actually checking the string. We repeat this again at position 6. We find again that the RLCP is lower than our R, so we know we have to go right, and we do not need to actually access the string itself. And finally, at position 7, we find that our RLCP is 4, which is now equal to R, so we have to compare again. Essentially, there's not much difference between this and a binary search, but the key point is that by having these two arrays, we save some of the string comparisons, which is a very significant part of the query cost if we have the strings compressed in some way. So by using this technique, we pay the cost of these two arrays, but we save a lot of effort in the computation of the string comparison. The reverse operation access, that is mapping an ID to the corresponding string, is essentially the reverse traversal in our binary search algorithm. We start at the corresponding position, we check the maximum of the values. In this case, for instance, the maximum is 4. So we know that at this position, we have the characters from position 4 to the end of our string. And then we move to the left or right parent following this binary decomposition of the string. In this case, we choose the right parent because we used the RLCP, the right value. So we would move to position 10 and we repeat. Now the maximum of the values is 2. We can take either one. So we can decode the characters for position 2 and 3. And we would move now to the left parent, that would be position 8. We find now that the maximum is 0, so we can decode the characters 0 and 1. So in this reverse binary search, we decode the string from the beginning to the end. In this case, we do not save string comparisons, but we can solve it easily using only the fragments of the strings after the prefix removal. Of course, we tested a number of implementations for all of this. In practice, we do not keep the collection of strings separate. We just concatenate all of them in a single sequence or a single string. And then we tested a number of solutions. For the arrays, we tested plain arrays, as well as arrays compressed with directly addressable codes. For strings, we also tested plain strings, as well as strings compressed with repair that obtain much better results than the ones that are shown here. With some specific implementations to provide direct access to each string in the collection. There are some other variations. As I said, the string terminators can be removed with adjustments to the query algorithms. We also tested implementations where we do not have the two arrays, but we only have one. This means that we save one of the arrays, but the string tails will be longer because our prefixes will be smaller on average. With all of these variants, we performed an experimental evaluation comparing the techniques that I described before, differential encoding and binary searchable DAGs, as well as path decomposed tries, which are a recent solution that is based on compressed tries that obtain very good results, especially in query times. We tested on web graphs and RDF datasets. I'll just go very briefly over the overall results that we obtained. These are the results for one of the web graphs. Essentially, our solutions are all the hollow elements that appear to the left of each plot. Since we obtain, in general, the best compression among all the solutions that we tested, notice that we have a lot of different variants. This corresponds to all of the implementation variations that I described before. Other solutions, as you can see here, such as PT, which is the black cross, and the full squares that represent binary searchable DAG, improve on our query times, but they require a bit more space. And the interesting part of our solutions is that we also provide a kind of trade-off, not within the same variation, because each variation corresponds to a single point, but our different variations can improve query times for lookup, for access, and or improve compression depending on the characteristics of the problem that we're trying to solve. These are the solutions for URIs in the RDF dataset DBpedia. The results are similar. We again obtain the best compression. We're not the fastest, but provide an interesting space-time trade-off. And notice also that the results represented with a line correspond to other solutions based on the same idea, on the same idea of front coding, and we easily overcome the results. For literal values, again, in RDF dataset, the results are similar. In this case, we obtain even better compression and are even more competitive in query times with other solutions. Even though we're never the fastest solution, we achieve significantly better compression. And that's essentially, as I described here, we propose a small new family of compressed solutions for a string dictionary. We dominate similar techniques and provide a good space-time trade-off compared with other solutions in the state-of-the-art. Of course, our solution is highly static. We've been looking into applications of similar ideas to a dynamic scenario, but that's not easy because of the binary decomposition that we impose on the data. And we're also looking to the extension of these ideas to other domains of operations. For instance, a relatively simple query that other solutions handle well is searching for a range of strings or a range of positions in the dictionary, which is not so easy to handle in our solution because of the binary search that we need to perform. So that's all. Thank you for listening. If you have any question, I'll be glad to answer them.
Well, thank you, Guillermo, for your talk. So you can raise your hand if you want to ask a question to the speaker. And yes, so could, in the different experiments you provided, you either tried to compress either a graph of URLs of websites or directly dictionaries, if I understood well.
Yeah, we test the URLs in web graphs, and in RDF, we test separate compressions of URIs for subjects, predicates, and some objects in RDF, and literal values that appear also in RDF data.
Okay, so I was wondering if in the case of the web graph, one thing that, well, it's a practical problem, but what we need usually is to have both the URLs, so a dictionary of strings that you can compress with your method, and also a set of links between the websites. So would that kind of structure be able to cope with that kind of graph structure where you have both strings and links between the strings? Or should it use two different kind of strategies? Or is there a way to compress both?
Yeah, the idea here is that we focus on the problem of the representation of the dictionary, because very efficient solutions exist that can solve queries on the graph represented as a matrix or any other kind of representation, but acting on IDs. If a representation can work with any structural graph to solve these queries without needing the string sorted in a specific order, for instance, our solution could be applied just as a additional complement to this kind of solutions. In fact, we have also worked on the structural part with other types of compressed representations that work precisely in this way. They assume that the links are between pages identified by IDs, and you perform all of the complex part of the queries and return again IDs. So adding this dictionary, we can simply translate the original queries, which are basically on URLs, into something that these other structures can solve separately, and we can translate back the results of these structures into something that the user is expecting. That's the set of URLs that are pointed to by the user. So that would be complementary to another solution that solves this structural part of the query.
Okay, I understand. I have another question, if unless somebody wants to ask. Well, one which is very practical, which is your code easily downloadable? Is there any library that can be used by the community?
We have a source code published in a Git repository.
Okay.
It includes most of the variants that I described here. There are some others that need to be configured when compiling, but it's ready to use and can be applied easily. So. And
another naive question, because well, I'm not so familiar with that kind of indexes. I remember Gonzalo's talks about wavelet trees, but it's been a long time ago. And would it make sense with your method to add things like trying, because here you either look at the left or at the right of the string saying that there are common prefixes or suffixes. Would it make sense to have parts of URL encoded also like this? Because you can suppose that, for example, all newspaper sites have the same kind of categories like sport and the kind of hierarchy that you can find in many sites. So the prefix is not the same, but the middle part of your URL is. So
you mean to try to apply compression to the middle part of the...
Yeah, or to include this in the indexing scheme, in the compression scheme as an extra layer, maybe a third index that would help compressing it even more. I don't know, just a naive question.
Actually, that's something that we didn't try. There's a lot that can be obtained there regarding compression, probably, but I don't know if it would be easy to combine with something that provides efficient direct access to each element. Regarding compression, there's surely a lot that could be done with these middle parts that are probably easy to compress, but the idea here is just to apply a simple compression idea to the prefixes. And also notice that in most of our variants, the string tails after prefix compression are again compressed using some other compression technique. In practice, we use repair in our solution. So after removing the prefixes, we're again compressing the sequence of concatenating all of this. So most of this can also be exploited by this additional compression. Maybe there's something that we could do specifically for that, but we just delegate on this well-known compression that should exploit most of this.
Okay, well, thanks again for your talk and your answers. And so we will move to the next presentation. Thanks again, Guillermo. So the next presentation, I hope the presenters are ready, is on the reproducibility of experiment of indexing repetitive document collection, and it's University of Coruña, Chile, and Valladolid, CNED, collaboration, and PISA also, lots of people. So I don't know who will be presenting this paper. Antonio? Antonio. We don't hear you, Antonio, yet.
Okay, I'm sharing it. One moment, please.
You are not sharing the...
Is it fine?
Yes, it is. So just go ahead.
Okay, I'm going to present this talk. It's about an experience of how to reproduce the results on a previous paper. I am actually talking about a paper we presented in Information Systems in 2006, this one. And we were invited to present how to reproduce the experiments there due to the large amount of techniques presented in this paper. So the idea is that how we work is that usually we have a good idea or an idea, and we try to, that we can explain it in detail. And then we create some source code and run experiments and possibly compare with the state of the art. Our experiments are good. Okay, we have a paper. But the idea is that in most cases, the results, the experimental results are the evidence that our achievements are correct. And maybe we have not think a lot of times about if we can repeat our own experiments. So this is the first thing. I want to repeat my experiments using my own setup, maybe the same machine, and surely I have to obtain the same results. This is about repeatability of experiments. Another term is replicability. The idea is that I can share my code and give that my setup to another equipe, to another group of researchers, and they can replicate my results. And a strongest way of repetitivity here will be reproducibility. That will be, okay, I have explained everything so well that anyone can understand what I did and reproduce my results. So that could be the idea. Okay, that was until June. Now in the ACM, they swapped the last two terms. So we talk about repeatability, reproducibility, and finally replicability. But the idea in this work is that we had a lot of techniques in this paper that was about universal indexes for large repetitive document collections. And we were invited to create a new paper explaining how to repeat all our experiments there. It's not that easy. So 1 year later, we forget about some source code. There were some dependencies that were not matched in the same computer because some updates were done there. Also, the operating system changed. So we tried to do that. So we gathered the codes and include the source data sets and query sets. We gather the exact configuration of the techniques, and that is not so easy if you have made some changes for small experiments after sending the paper and receiving a minor revision and that stuff. So what we try to do is to prepare scripts to drive all the experiments and try to automate as possible the process of running experiments and getting the results and preparing the images of the comparisons that we have to include. Finally, apart from that, it is a good idea to recreate all that stuff in a virtual environment. It could be a virtual machine or, in our case, a container, so that anyone could try to reproduce our results quite easily. And it is what we did. In the parent paper, what we had is a set of inverted indexes. So we had an inverted index that were indexing a document collection that was compressed. And for inverted indexes, we had several variants. We had a full positional scenario where we were pointed for the positions where a 10 were occurring within the documents, or just to document IDs. And we were about to search for words, phrases, 4 types of patterns here. And we wanted to compress the collection and also the posting list. For compressing the posting list, we used the typical ideas. We have a posting list, an increasing sequence of integers. We apply up encoding, and then encode using variable encodes. In some cases, some techniques, we add also sampling to speed up intersections. So that's the idea. How many versions variants did we have for this inverted index? Well, we had 22 post-integer representations in the non-positional scenario, a few less in the positional scenario, and some of these, in particular these ones, were new techniques. So we had inverted indexes to perform searches, and also we had the document collection compressed with a grammar-based compressor, repair, that had very, very strong compression in repetitive scenarios. So we have the ability to extract any part of a document or even the complete documents. Apart from that, we also include self-indices in our comparisons. So we have a self-index, which is basically a compact data structure that includes indexing capabilities and also keeps an implicit representation of the data in the same structure. By keeping the index and the document collection itself, we can query for a given pattern and also extract any part of the collection. And in particular, we have 6 different self-indexes. 2 of them were new here, and the others were from the state of the art. So what we did in the parent paper was to run experiments, and we ran a lot of experiments. In the non-positional scenario, we had inverted indexes, and we tried several different techniques from the state of the art, all of these, in 4 different configurations. Then we compared those inverted indexes with our variants, and we could see that, okay, our variants designed specifically for highly repetitive document collections obtained much better results in compression. They were typically slower, but they were able to reach very high levels of compression. And then we also tested the positional scenario. So we used the traditional inverted indexes on the one side, and then we compared that with our representations and also with self-indexes. Finally, we also measured, that was for locating patterns. We also included extraction times or extraction experiments to recover the original data from the collection. That was the parent paper. And what we tried to do was to repeat all the experiments there on the first time. So we create a framework, which is published here, where we included the source code for all the techniques, the document collection itself, also the query patterns we required. And we included scripts to create the compressed representations of the source data using the different source code variants. So we had different compressed indexes, and then with the queries, we performed both locate queries and extract queries. After that, we had a lot of files containing query logs or data files with the output results that we used as usual to create the figures and the tables we wanted to include in a report that would contain all the experiments, figures, and tables with all the experiments that appeared on the parent paper. But that could be run in a different computer, so we have probably some differences in time, not in space, but yes in time. The structure of our repository is something like that. We have the data, the indexes, the inverted indexes in the non-positional and positional scenarios, and then the self-indexes, and a lot of scripts to automate all the tasks. Finally, we have also a reporting tool, which is basically a LaTeX template and some scripts to gather the data obtained along the experiments. So the steps of this framework was basically including the source code and compiling all the source code for the different structures. This was kept in different directories, non-positional indexes, positional indexes, self-indexes, and for each of them, then we managed to take care of the dependency so that we knew exactly which code was required to compile our sources, and then we managed to have a build and a search program that could be used to create a compressed representation of the index and also to perform queries. After that, we also packed the data from the source data from the collection. We used a version of the Wikipedia, the English Wikipedia archive. It was included here. It was only 200 megabytes because it is actually very, very repetitive. And we used two different subsets of this part, one using this size and another one using around 2 gigabytes for the positional scenario. Also, we include all the query sets we required for locating patterns and also for extracting queries. After that, we performed the indexing step that for each, where we included a script for each technique, where we used the data collection and we create the index. And the index was created in memory, but they was finally written to this so that it was persisted there. Basically, this was done by creating scripts that, considering all the configuration parameters of the indexes, created one or more representations that were written to this. This was important. For each technique, we have to know which parameters have at pooling time, and we need to know which were the exact values that we have been using in the previous paper. So these are the configuration parameters that are also included in our replicability paper. So we create the indexes, we have the indexes set into this, and now we can perform queries. We load the index into memory and perform queries. So obtaining, well, this is already done with a new script that is in charge of, for each configuration of each index, it performs the queries that we are trying to perform. So the result is a set of files can contain output data created by our programs or just executing logs. In one cases, in our experiments and the techniques we create, we managed to have that all the output of the programs have this shape. So we have index the size, the milliseconds per pattern, the microseconds per occurrence, the occurrence, and so on. And in other cases, what we have is an execution log that we had to parse in order to create a data file that we were interested in. So in the end, we had a lot of files, including results for the different techniques. So using that, we can start to recreate the same structure of the parent paper. So all the figures in the parent paper were now reproduced. For each of those figures, we create a directory, including basically a script to go through along all the different data files along the directory structure and copy all the data files to that directory, and then using a ggplot, in our case, as in the previous paper, we create the image associated to those data. So we have one figure, we repeat that for all the figures in the parent paper, and we were able to create a final report that will have this shape. It is a PDF obtained using LaTeX with some text, with some explanations. All the figures that have been reproduced along the executing of our framework, and then some additional information. For example, we have machine features and configurations. We have run all our experiments in a new machine, so it's important to know the type of machine, how much RAM, the operating system, and so on, in order to be able to compare the figures in the parent paper and ours. It should be probably different. Apart from that, we included additional information the reviewers asked us for. For example, how much time does it take to build an index or to search all the possible patterns for a given index? That is very easy. It's only each time you enter a directory to run the queries. Yeah, I'm finishing. the queries of a given index, we put a timestamp. Each time we end that script, we close that timestamp, and we can create something like this. For each index, we know the indexing time, querying time, and also if the test worked fine there. And that will be the workflow we handle in the reproducibility paper. Finally, that will be enough to perform reproducibility, so we can reproduce a file. Yeah, I'm finishing. To repeat all the experiments in our paper, to allow reproducibility, it is much easier to take that and put that in a virtual machine or a container. We chose Docker because it is very easy to install and it's very easy to configure. Basically, to create a Docker container, we have only to create a Docker file that is something like this. It's a text file. I don't know if you can see it. It's a text file when you basically indicate which image from the repository of Docker images you want to use. For example, in our case, Ubuntu 14. And then you can run some commands within the container, so you can install all the packages you need, and then you can add additional stuff. In our case, what we did as additional stuff was creating new user to run the experiments, installing SSH server in order to connect to the container, so that using the container for anyone not using it before is so easy as connecting by SSH to a remote server. So it's very easy. And that's it. What we have to do to create a container is to create that Docker file and then create our image. We use Docker build using this Docker file, and then we have an image with all the stuff we need there. And finally, we start an instance of the container by using this. In our case, this part of here is only to enable the SSH connection here. So finally, I can connect to the machine and run the experiments there. And after maybe 1 day or a little more, I have all the experiments reproduced there. And that's it. So as conclusions, I'm sorry I'm a little bit late, I think. The idea is that if we want to repeat your own experiments, you have to try to be ordered the first time. I was not in the previous paper, and I tried to manage to do that here. It's important to provide the source code, data, queries, and suspected, but also, and that is not included in many papers that we can see, the actual parameters for the techniques that are included in the experiments. Also, just considering that maybe we are sending a paper to a journal and we have maybe 1 year later a response saying, okay, you have to make some new experiments or repeat some part, it's important to try to automate that as much as possible. Creating scripts for running the experiments and also to generating the reports, the figures, and whatever. By doing so, we have repeatability. If our computer breaks in that time, we need also reproducibility. Or if we want to share our experiments to another one, we have to provide reproducibility. And using a container simplifies this very in practice. And that's all. Thank you for your attention.
Thank you, Antonio. You can, as always, raise hands if you want to ask a question. Okay. Well, so we don't have much time, so just time for 1 or 2 questions. So what you presented is basically what you did to reproduce experiments on 1 paper.
Yeah.
But no, the question is how could you translate this into, well, or maybe to reformulate the question, what are the important key points in what you did that you think that would be useful for others to reproduce whatever computer science work? Are there messages or things that you learned throughout the process that would be general enough so that
Yes, I think that the key point is to be well organized and try to automate all the steps you are performing when you run your experiments. In in our case, the problem was that it was a project that started maybe 4 years ago, 4 years before 2016, and it was increasing. So we started with a small collection, then it moved to a larger collection, and when you have different techniques, maybe you are making different changes. And in some cases, for example, some techniques requiring much memory to index. So we moved that to a different computer, and then we set there the parameters of the indexes, and then we moved them back to the testing machine. At some point, some parameters were missed. So maybe it was my fault. I was not very ordered at that, but many times we are doing the things with so fast due to hurries that we are not considering that someone has to reproduce this maybe 6 months later, or you have to repeat your experiments 6 months later. So it's important to try to create your experimentation in such a way that you can repeat that and you can compare the actual results quite easily. Not only generating the output files, but also creating figures, it's a good point for.
Okay, so the main message is to be organized, if I understand.
That's the key point. And then for sharing things that are complicated to handle, maybe in our cases, some indexing performed for some techniques required several steps, because some of the sources were not developed by us. So we have to shift our query patterns in order to match the requirements of others. And sometimes that is done only once. Okay, that works. I have the results, but later, keeping that in a well-organized it's the important thing.
Okay, well, thanks again, Antonio Farinha. We will move to the next paper, which will be presented by Florian Boudin, and it is about the DELIS project, which is indexing scientific literature through semantic expansion. So it's a joint work with between Nantes, Nancy, and Montreal. Florian?
Hi, can you hear me?
Yes.
Okay, so
go ahead.
thank you. So today I'm going to talk about the DELIS project, which is a project funded by the French National Research Agency, the ANR. It's a 4-year project, and it involves 3 partners, Nantes, Nancy, and Montreal. This is okay. This project only started in January this year and will end in 2024. So I will describe the project in its very early stages. And I will just present what we are planning to do for the next 4 years and what we have done last year about indexing scientific publications. So let us start with a little bit of context. We all know that searching for relevant publication is becoming increasingly difficult and time-consuming. There are many reasons for that, but the main reason would be the explosion of the number of scientific publication. We publish more and more scientific articles every day, and it's difficult to manage that kind of amount of data. Another reason for that would be the current practice in paper indexing that often use only a part of the scientific article. By part, I mean the title and the abstract, that for licensing issues or for computational resource limitations. And one way to alleviate that, to improve retrieval of scientific papers, is to use key phrases to supplement paper indexing. So key phrases are keywords or word or phrases that best describe the content of a document. However, very few documents, very few scientific articles come with associated key phrases. and the manual annotation of such a large number of documents is simply not a feasible option. So we witness a surge of interest in automatic key phrase generation, and many models were proposed over the last 2 decades. What we saw in the literature is that these models have 2 main issues that may prevent them from being used in practice. So the first issue is that the state-of-the-art models that are all neural-based models still achieve very low, relatively low precision score compared to other NLP tasks. So these scores are in the mid 20 or 30% of precision, which is quite low. And another issue is that these models are not able to accurately generate key phrases that do not occur in the documents. These are called absent key phrases, and they are very important for document indexing because they expand the semantics of the documents and they allow to better retrieve the documents. So the goal of the project DELIS is to solve these issues by improving and enriching paper indexing using what we call semantic expansion, that I will explain later. The originality of our approach is that we use a graph-based ranking model at its core. So this allows us to have more flexibility on how to improve the ranking and how to inject prior domain information. And one way to do that, to inject domain knowledge, is to identify semantically similar documents in the collection and use that information that is contained in this set of documents to improve the term rating scheme and to index new terms that occur in semantically similar documents, but that do not occur in the document that we want to index. So I will present the 2 challenges, how to improve the ranking of key phrases and how to enrich the indexing, and I will present the solutions that we aim to do. And yes, the 2 challenges, and then I will present some of the preliminary results that we obtained just before Circle. So to improve key phrase ranking, what we know is that the content of the paper alone is not sufficient to effectively rank key phrases. We have to find more information about the domain, about the use of terms, and we have to inject that in the model to make better predictions, sorry. But here, as we use a graph-based ranking approach, we have to ask ourselves where and how much information would be injected in the model. And that's very important because if we inject too much information, we have a risk of drifting away from the semantics of the original document. So the solution, what we propose to do that, is to find the weakly connected components in the graph and introduce or straighten the edges between terms that co-occur in the related documents. Here, the idea is to take information from the related document and enhance the information from the document we want to index. The other challenge is to generate key phrases that are not present in documents. So as I said earlier, these absent key phrases are very important because they expand the document and they alleviate the vocabulary mismatch problem that we are faced when we do information retrieval. What we know is that state-of-the-art neural-based models achieve very low accuracies on absent key phrases. There are many reasons for that. The first would be that it's more difficult. It's a larger search space. Every term can be generated. And also that these models use an output vocabulary, so the predictions are bound to this fixed-sized output vocabulary. So these models are not able to generate any phrases, but only a small subset of possible phrases. So the solution that we propose to tackle that is to use the semantically related documents and to mine new terms within these documents and expand the graph using these new terms. And hopefully these terms will be well ranked and will expand the semantic of the document we want to index. So I will present some of the results that we obtained earlier. So the first work that I want to talk about is that if we looked at the literature on key phrase generation, we can see that there is a lack of unified evaluation methodology. So if we compare the papers that were published over the last 10 years, we can see different benchmark datasets, different baselines, different evaluation measures. So it's very difficult to have a grasp of the current state of the art on that task. So what we have done is we conducted the first large-scale analysis of state-of-the-art key phrase generation models involving 9 benchmark datasets from various domains. So we used newswire articles, scientific papers, so full papers, and abstracts. And we also use different annotation sources, so author-provided key phrases, indexer-provided key phrases, or reader-assigned key phrases. And we contrasted 9 models, very simple baselines such as TF-IDF, ranging from these simple baselines to state-of-the-art neural-based model with seek-to-seek copy and attention mechanisms. And we compared these models on a standardized evaluation framework using well-known measures as F-measure and mean average precision. So the findings that we provided in this study are, we saw that neural models, very large-scale neural models, are still challenged by simple baselines of some datasets. So that is due to the fact that these models are not easily, how can I say it? The generalization capacity of neural models is very limited. So if we apply this model on different type of documents, we have very poor results. We also saw an evaluation or training bias when we use author-provided key phrases, because those are very noisy. So when we evaluate using that kind of data, we can miss good key phrases or we can learn bad key phrases. And we use that large-scale analysis to make recommendation on which baseline and dataset you should use in your future work to have strong findings. Another set of works that we have just finished is we collected a large-scale dataset of newswire articles with professionally indexed, professionally assigned key phrases, and we conducted an analysis of the transferability capacity of neural models on the news domain. So that's one thing that we have done, and the other thing is we studied the impact of using key phrases for document retrieval. So that was a work that was presented yesterday at ACL, where we compared the effectiveness of several retrieval models with and without key phrased indexed. And what we saw is that key phrases are helpful for document retrieval, even to a surprise when gold key phrases are provided. That means that automatically generated key phrases can act as a proxy for gold key phrases or can supplement gold key phrases. And we also provided in this study an extrinsic framework for evaluating key phrase generation models and better understand the strengths and weaknesses of these models. So I will conclude by saying this is an early stage project. This is the website where you can find all the information about what we are doing here. The resources, the models, and the data sets are in this URL. And if you have questions, you can ask me or send me an email to that address. Thank you.
Thank you, Carol. Well, as always, if you want to ask questions, you can raise your hand. Okay. So I will start. Thanks for your talk. And it's quite okay. So go ahead, Josiane.
So my question is, so the ground truth is not, I mean, usually the ground truth is based on the author key phrases, for example, for the scientific papers. What do you think about this ground truth? And can you, I mean, do you have some ideas to improve this ground truth? And I want also to mention that I really like the idea of enriching the way you do the existing key phrases.
Well, thank you. About the author-provided key phrases, what we saw is that these are very inconsistent. We can see that there are many ways of, for example, saying neural networks. So if you look at author-provided key phrases, you will see neural networks, neural models, neural things. So there is no unified way of assigning key phrases for authors. So one way to improve that would be to do what they do for newswire articles. It's using a semi-supervised model to propose key phrases to author, and that they select these key phrases and maybe add some new key phrases. So I think that should be a semi-supervised way of assigning key phrases to improve the quality.
Thank you.
And well, I know I could look at the papers, but among the different techniques that you use to extract key phrases, which were the most successful?
Well, the most efficient ones are neural-based models, but they require a lot of data to be trained on, and they are only efficient on the type of data on which they were trained on. So,
yeah, it's machine learning things.
Yeah.
But how do they work in general? Is it an extractive or a generative process, or both? And in which case, which are the best?
They can do both. They can extract key phrases and generate key phrases. So it's a seek-to-seek with copy and attention mechanisms. So you can extract key phrases from the content or copy new or generate new key phrases from an output vocabulary. But when you generate new key phrases, these are very bad. The model is not able to do that because it's too hard. You have too few the content of a document to generate good candidates. So
yeah, I guess
that's one issue.
I don't know if it's the issue, but I guess that when you have to generate diverse sentences, it's quite hard. I mean, doc to query just generate terms, which is kind of easy. But if you have to generate diverse set of sentences which are diverse, it might be a bit harder to train, and maybe I don't know if it's one of the issues or.
Yeah, we need domain information. We need more information in the model to generate better phrases. That's for sure.
And with respect to the second part, which is retrieval, and what kind of strategy did you use to exploit key phrases? Did you just add them, concatenate the document with the key phrases, or did you have more sophisticated ways to do so, to combine them?
It was a very simple way where we expand the documents with automatically generated key phrases, and then we indexed those documents using a retrieval model.
Okay, so standard
yeah,
BM25 or with neural based models.
We use BM25 and query likelihood with pseudo-relevance feedback, but we can still apply a neural-based re-ranker on top, and the result would be, I think, the same.
Yeah, I don't know, because for instance, when you look at the results with passage retrieval and BERT-like approaches, you see that they are good at it because they kind of fill the semantic gap between passages and questions, because passages are very small, sorry, short in size. So I don't know. Yeah, it's not for scientific papers. I guess the problem is not the same. So it's
yeah, maybe
might add some important words. Yeah. Okay. If there are no other questions, we will end the session. Thanks, Florian, for this presentation, which was very interesting. And well, the next session will start in 15 minutes. And will be about user profiling and interaction. So see you over there. And maybe there is I don't know if there is a room for the break.
People are not using that, so people are not using
they want to make a break.
So you can stay in this room if you want to chat, or if some people want me to open some rooms, I can do that.
Okay. Thanks a lot again to all the participants, and I'll see you in a few minutes.
Monica? Oops. Yeah.
Hello, Yusian.
Yes.
Yes.
Go to the chat, please, because here I have a lot of echo because I have a speaker.
Okay.
So could you go to the chat, please?
Yes, of course. Hola, Alex.
Hola. Hi. Do you want to try the slides? Okay. So Fernanda, you are presenting the first paper, right?
Sorry, Alejandro.
Yes.
just trying all the connection, and then I will give you the floor.
Okay, perfect.
I'm fine. Oh, how do Hello, does it work? Okay. Thank you. Stop. Okay. I'm fine.
Fernando, can you please talk a little bit?
Yes. Can you hear me? Hello?
Yes,
Can you
yes.
hear me?
Yeah, we can hear you.
Okay, perfect. Thank you. And you can see also my presentation?
Yes.
Perfect. Thank you, Alejandro.
So now is missing the second presenter. Please, can someone raise her hand? I think it was Clara, but I cannot see you. Is there any presenter for the second paper?
Okay, who is presenting the third paper?
Monica.
Monica.
Yeah.
Okay.
The third paper
And the
is-
last one?
Can you hear me?
Yes.
Perfect. And I just tried and I managed to share my slides, so I'm very happy. Thank you.
Yeah. Okay, perfect. And the last one is sorry? Ah, hi.
The last one is me again.
Ah, okay. Okay, perfect.
It's easy.
Okay, good.
So it's for the last two.
Okay.
So we have still the second paper without any presenter. Normally, this is Clara who is supposed to present the paper. We did some tests on Monday, so I think that she will show up. We will see, and I will tell you, Fernando. I will tell you when she appears. I mean, when she appears, I will chat you. So please be aware of the chat. Did you manage Alejandro, did you manage to see the chat? Because I'm chatting to the session shares. sometimes.
Yes, yes. I see the chat. I have it here. Okay. So Clara is already here. Clara, do you want to try the slides before we start? Yeah, let's wait 1 or 2 minutes.
Okay.
So Clara, you are now the presenter. You can try the slides, and so that we can move on and start the session, please. Okay.
Sorry, I can't hear you. You are muted.
Okay. Okay, yes. So Fernando, please put the slides. So welcome everyone to the last session of today about user profiling and interaction. So the first paper is a short paper. The title is in Spanish, but I think it could be translated into topological similarity between users, application to recommender systems, by Fernando Diaz, Alejandro Bellojín, myself, and Jesus Serrano. So Fernando is going to present. So whenever you want, you can start.
Okay, thank you, Alejandro. Because I have no camera on my desktop, when I finish my presentation, I'll try to connect with my tablet. Okay. Afternoon. Greetings from Madrid. Thank you everyone for staying connected. My name is Fernando Diaz, and I'm going to present the work entitled Users Topological Similarity, which was developed with Jesus Serrano and Alejandro Bellojín. This short paper dives into a different conceptualization on the user profiles comparison by means of topology. Topology, in brief, is a branch of mathematics devoted to the geometrical properties of objects. All of us have played some time in our childhood the popular children's game of the 7 differences. If you remember, it's about finding the differences between 2 almost equal images. Let's go. Find one of the differences. You find one, some. Okay. But what it is so usual is to play the opposite game, the game of similarities. Come on, now spot the similarity between the 2 images. Does anyone find it? Some solution? Okay, here you have the solution. A cup, a donut. A cup are logically equivalent. What does this mean? Both objects are equivalent from a topological point of view, as you can see in this picture. Imagine that the cup is made of plasticine clay. You can deform it with your hands to generate a donut. This start of new alternatives on profiling. We will review brief notions on topology, as well as the computation of users' barcodes to compare profiles. This presentation, we are going to talk about data and topology. In recent years, a discipline called TDA, topological analysis, has become popular. It's part of large volumes of data to try to understand the shape of the data. It is also typical shapes, for example, or called patterns, topologies that are invariant under small deformations. Objects and their variations are studied in the face of small transformations. In this sense, in the previous slide, we saw how a cup is easily transformed into a dana. To understand the data, we will see in the following some elementary notions of the characteristic geometrical structures. A simplex can be formed by a point in the space. For example, this is a simplex, or a small joined by segments and with faces. This is also simplex. And complexes join or not among themselves. For example, this is also a simplex. In general, we call these structures, these complex structures, are called simplicial complexes. Let's see complex in more detail. In complex, we have 0 simplex, which are points, 1 simplex, segments, 2 simplex, bidimensional holes or n-dimensional holes. Very that characterize complexes. In the example, the numbers 1, 1, 0 correspond to one connected or complex one with one bidimensional hole, this one, no n-dimensional holes. A couple more examples. We can see a couple of complexes. The one on the left has a number, Betty numbers, 1, because it is characterized by 1 with a hole and 0 n-dimensional holes. The one on the left right has very number 0, 0, which means 2 complexes and this 0 bidimensional holes and 0 n-dimensional holes. In the second example, regarding the cup and the dana, both objects share the same very numbers, 1, 1, 0, so they are equivalent. To compute simplicial complexes, and quite simply corresponds to the so-called Viettori strips. Starting from the points that represent our data, we draw a sequence of balls of increasing radius, observing the evolution of the simplexes that are formed, their connect, the holes, etc. In this case, in the future, we can see how, when passing from radius to radius, we have balls of radio epsilon 1. Here we have balls of radio epsilon 2 that is greater than epsilon 1, etc. Then the algorithm joins the corresponding points with segments when 2 of these balls intersect. In this case, we have a more complex simplicial formed by about 15 points, and we have also 5 points that are unconnected. We continue increasing and finally some 3 holes, and when we increase the radius of the balls, the holes disappear and the Viettori strips complex is the topology of a point set. We see the process of moving from user profiles to their topological representation as barcodes. We compute its similarities. In our dataset, the user profiles are characterized by different attributes such as gender, age, or music tastes. The user has favorite directors, actors, actresses, genders, and also ratings of the items that the user consumes. Use the information of the user profile to generate a cloud of points that it describes to him or her. From different clouds of points. Here we have a user with a cloud of points. Here we have a new user with a different cloud of points that represent or that characterize him or her. Now, we will compute the barcode that characterizes. Code is just a bidimensional representation of the cloud. Example, we start at radius 0.5 with 20 unconnected points. Here you have the points and 20 also 20 bars that represent these 20 points. If we increase the radius of the balls to 1, 20 points remain unconnected, so continue having 12 bars. When we reach radius 1.5, we already have the complex points and another 5 unconnected points with 6 bars because we have 6 elements in our complex. Also, here labeled as 1, which is represented with this red bar. We on adding ready, we see that the second holes. Here the second hole appears when we increase the radius, and now the third hole appears also. At the same time, when continuing increasing the radii, the holes disappear until they are reduced to a. So there is only 1 bar, as you can see here at the end. We have without holes. Oh, this is a barcode that represents the user, the points that represent the user. We use the barcode overlap metric. It is on the Jacquard similarity coefficient. In the A and B represents user barcodes. The extended version of takes into account the cases of empty sets when the A or B or both are empty. Formula, we average with of the kernel of the sets compared and the barcodes. To perform the barcode comparison, the previous diagram representation, here you can see the user A, the user B with their barcodes, and every bar of each user with all the bars of the other user, and vice versa. We obtain the values of the supreme of the intersection, and then finally we sum up and average with the cardinals of the two sets. This gives us the metric called barcode overlapping. We some experiments with the data set multi-lens 100,000. We represent the users by their pairs, item value. We restrict to users with less than 50 ratings, comparison concerns. To compute the barcodes, we use the JavaPlex library, which is an open written in at Stanford University. To make, we rely on a standard KNN algorithm. In these two images, there are representations of a user with two different radii, a square root of 2 and a square root of 8. And you can see how the ball intersecting between them, and when in that case a segment appears between the points that represent the user. Here in this slide, you can see the barcode associated with the previous user, with this one, at radio square root of 2 and a radio square root of 8 with their bars. And in this picture, we can see that there are no holes at all. Well, experiment, the results of the recombination are shown in this table. We have used different similarity metrics, such as the SBO with different parameters, and Pearson metrics, implemented a random. As you can see, the results are not bad. They can be directly competitive, at least, or two of the use metrics. Well, and that's all to remarks. This is a work in a very early stage. We are still studying necessary basic concepts. However, we have been able to perform a simple experiment of behavior comparable to other standard similarities, Pearson or Cousin, but due to additional restrictions we have to deal with, this topological-based approach can be useful for situations like the star problem, where there are little user data. Our experiments to other data sets, as well as other algorithms based on graphs or to optimize the process, etc. And we also must improve the computation of the bar similarity, which is highly dependent on the dataset size. And well, that's all. Now it's time for questions. I will try to connect my tablet.
Okay, thank you, Fernando. So now we have some minutes for questions. So I don't see any hands raised here. So anyone who wants to ask something, just unmute yourself and
Alejandro. Hi.
Yes, Ivan, please.
Yes, this is okay. Thank you. So I do have a question. Fernando, which is the space you consider in your experiments? I mean, which is the data you transform from the user to this barcode representation? Are you using ratings? Are you using content-based features? And how do you make the process to convert them?
Yeah, yes, we could only, sorry, because I'm We have echo. In our experiment, we considered only ratings. We use the movie lens dataset, and we considered only the ratings of the of each user to the items he or she already consumed. Consider the use of other data that represent the profile of the user. As I explained during my presentation, we can use information like their location or their sex or gender, etc. But we haven't done any try at all at this moment. We are understanding with topology we can represent in a metric space, we can represent the information of in this case a user of a system.
Okay, thank you.
You're welcome.
Which is the motivation behind this idea? Which is the motivation? Which could be the difference between this kind of similarities between other similarities that are usually used, no? Like Euclidean distance in the area.
That's the point, because all the and are based on Euclidean metric. So we are familiar with measure between points using a rule. But when we deal with topology, we talk about properties, invariant properties of objects. So we compare users like objects. They are they have a shape in the space, probably in a n-dimensional space, because now imagination we are we want to deal with the representation of a user in an n-dimensional space with many features of the user. So we want to compare objects and properties and invariant properties of these objects, not only the distance, the usual metric distance between points in a metric space. I don't know if I understand this explanation.
Yeah. Yes. Thank you so much. It's a very interesting work. Yes. So thank you.
The key point is the cap and the dana. They are similar because they have only one hole and they are similar objects. You can, if you model one with the other using some plastic, you can go to one to the other in any direction easily. They are similar objects.
Okay, thank you, Fernando. We still have time for one more question. If anyone wants to, anyone has any question? I have one. I was wondering, probably was more linked to the first question, or at least to the first answer you were giving to Ivan. But which challenge would you say is the biggest one when applying topology to recommender systems?
First, understand what topology means and how things change, and a user is quite different in terms of matrix of ratings that join users and items, and now we have objects with shapes in the space. And the second one is I explained during my presentation the computational problems or concerns, because well we perform a first approach to this problem, and we check that it's hard to compute all the barcodes for each user, then that's the reason, because we restrict it to users with less than 50 ratings. But there are alternatives. There are many other algorithms to compute barcodes, and we want to explore new ones.
Okay, thank you very much. So let's move to the next presentation. Thank you, Fernando. So, okay, I see Clara is already as presenter.
Hey, can you hear me?
Yes, perfectly.
Okay, great.
So now Clara Guénon is going to present an extended abstract called Resume, a robust framework for professional profile learning and evaluation.
Absolutely. So can you see the slide?
Yes, we can see them.
Okay, yes. Very good. So good afternoon, everyone. My name is Clara Guénon de Forson de Gabriac, and I am a second-year PhD student at the Leipzig lab of Sorbonne University in Paris. My work primarily focuses on representation learning and natural language processing, and today I will present my work called Resume, a robust framework for professional profile learning and evaluation, or just Resume for short. Let's begin with some context. While looking for a job has always been a preoccupation, we live in a world where the tools to either build a resume, apply for a position, or select relevant candidates are getting more and more numerous and developed. That being said, their diversity and lack of common standards makes it increasingly hard to find the right way to obtain the job that you want or to find the profile that you're looking for. This constatation motivates us to learn how to represent the career of a person in order to extract what we call their professional profiles in a way that allows for standardization and easier matching of candidates with jobs. We implement this objective by using the information available on a person's LinkedIn profile to learn and evaluate their professional representation. So this is a screenshot of a LinkedIn profile. As you can see, there are different types of information. On the left side of the image, you can see 3 professional experiences that we call jobs that are chronologically ordered. You may notice that a job is composed of a title and sometimes of a longer description. Note also that it is formatted in a very specific way. It has bullets, lots of nonverbal sentences, and it contains a lot of named entities such as company names or product names. On the right side of the slide, there are the user's skills. If you're a LinkedIn user, you know that you can fill in your skills and your relations will endorse you. Something else that you may notice is that there is some redundancy in the skills of this profile. You have, for instance, marketing, but also product marketing, digital marketing, online marketing, and so on. So the information available on a person's LinkedIn page is heterogeneous for one and semantically very rich. Proper representation of such data could yield numerous applications such as expert matching, personalized profile coaching, standardization of professional profiles, and a lot more things. However, the previous slide highlighted several challenges associated with the use of a LinkedIn profile. The data is noisy, it is user-generated, it can be partial and or corrupted, and it's written in a very specialized style. What I mean by that is that you do not write an email the same way that you write your resume, your CV, or a LinkedIn profile. That being said, the professional experiences of a profile are semantically extremely rich and, in our opinion, actually rich enough to allow us to learn a professional representation. Additionally, we can take advantage of the skills if we consider them as categorical data and use them for supervision and evaluation of the professional representation we learned using the jobs of the user. My presentation is classically organized as follows. I will go over the previous related work and bibliographical inspirations of this paper before presenting our contribution resume. We will then talk about the experimental settings and results of this work, and finally conclude and discuss future work. So let's begin with our reflective work. As I mentioned earlier, our intuition is that we can leverage the information contained in the textual data of a LinkedIn profile in order to build a user's professional representation. This naturally leads us to language models and word embedding models. In 2013, the algorithm Word2Vec provoked a genuine breakthrough in work embeddings by presenting a skipgram-based model that captures the semantic relationships between words. Later on, in 2016, it is the fast text algorithm that made a breakthrough by addressing one of the major limitations of Word2Vec, which is the handling of out-of-vocabulary word. The way they do so is by not representing the words themselves, but by representing the subwords that compose the words. Lastly, in 2018, Elmo proposed a contextualized word embeddings using a bidirectional LSTM, whose promise is to adapt the embedding of a word to the sentence context. In this work, we will compare fast text and Elmo in order to find which one can best capture the professional semantic of a user. Let's now move on to the solution we propose, the framework resume. On the left side of the slide is a schematic illustration of a user's LinkedIn profile. It is composed of their skill sets, the industrial field that they work in, and lastly, their jobs, chronologically ordered. So in the purple square, the first line of the jobs corresponds to the word sequence of their first job. Similarly, the second line corresponds to the second job, etc. You may note that the last job of the user is not used to construct their profile, but rather as an evaluation label. I will explain this further in the next slides. So, as I said before, the main intuition behind resume is that the past jobs of a user can describe most of the user's career because of the way you write about your past experiences, can tell a lot about them, depending on the vocabulary you use, for instance. Say, if in my resume I write that I can do Java and SQL, you as a human can understand that if I'm not a developer, I am at least very tightly linked to the computer science industry. And that's the whole intuition behind resume. This is the reason why we use the professional experiences of a user to build their profile. And we use the rest of their profile information to evaluate the representation that we built. In a nutshell, we build the user's representation profile ZU using their first jobs in purple on their illustration. And then we evaluate the obtained representation ZU by learning how to retrieve the user skill set, the industry that they work in, and finally, to generate the description of their last job. That is to say, to generate the word sequence that describes their last job. You will understand that this is, of course, a proxy to predicting a user's future job. Let's take a closer look at the model. So the profile building part of the resume framework can be broken down into two smaller parts, the word aggregation part and the job aggregation part. It is in the first half, word aggregation, that we compare the word embedding models, fasttext and Elmo. Note that we consider two versions of fasttext, one trained over large traditional corpuses of text, referred to as fasttext pre-trained, and one that we train on our dataset that we refer to as fasttext CV-oriented. The motivation behind those two versions is to find out if non-specialized NLP models can capture the professional semantic of a professional profile, or if, on the contrary, we need specifically trained models in order to do so. Another motivation for comparing those three word embedding models is to evaluate which one is most robust to the noisiness of the data that we explained earlier. The representation's robustness is also directly measured in the evaluation part, where we compare the results obtained from each representation on three very different tasks that are the prediction of the user skill sets, the classification of the user in an industrial field, and the prediction, the generation of their last job. Let's move on to the word level aggregation strategy. So as I said, the objective of this work is to compare different word embedding models. So the aggregation method is arbitrarily very simple. Each job is defined as the average embedding of all of its words embedding, either given by fastText pre-trained, fastText CV-oriented, or Elmo. Similarly, a user is defined as the average embedding of all their jobs. Let's now move on to the experimental results. So again, we evaluate the professional representation through 3 tasks. The classification of the profile in an industrial class, which is a classic classification task. The prediction of a person's skill set, which is formulated as a multi-label classification. And finally, the generation of their last job description, which is text generation task. Now, while the metrics associated with the classification tasks, the accuracy and the F1 score, are quite common, the blue score, however, used to evaluate the text generation task, is more specific to machine translation and automatic summary. The idea of the blue score is to count the number of n-grams that the generated sentence has in common with the reference. This example that I'm showing you here highlights both the purpose and the limitation of the blue score matrix. Let the reference sentence be, Bud Powell was a legendary pianist. Out of the 3 candidate sentences, the first one, which is identical to the reference, has a perfect blue score, which is 100. However, the second candidate, which is semantically closer to the reference, has a lower score than the third one because it has more words in it, and that is something that the blue score penalizes. So in short, the blue matrix aims at measuring the resemblance of a generated sentence with a reference, but fails to evaluate the semantic similarity. So as a reminder, we compared 3 word embedding models: a pre-trained ELMO to evaluate the relevance of contextualized embedding in the professional profile context, a pre-trained fastText to measure the impact of subword embedding on a specific setting that is professional writing, and finally, the CV-oriented fastText that we trained on our data. We also built a statistical baseline that we refer to as most common. So in the classification task, it is rather straightforward. When it comes to the industry classifier, the most common baseline always outputs the most common class across the data sets. For the skill predictor, it outputs the S most common skills on the data set, with S being the average number of skills per profile. And finally, for the next job decoder, the most common baseline outputs the N most common words across the data set, again, with N being the average length of a job description. So we presented the classification task and the text generation task in 2 different tables. What we can see is that on all 3 tasks, the CV-oriented fastText performs better than its 2 other counterparts and baseline, except in the text generation task, where the most common baseline has a better blue 1 score. You will note that the blue score that I mentioned earlier is here detailed from blue 1 through blue 4. The normal blue score expresses the overall resemblance with the reference, while the N accounts for the number of n-grams in common with the reference. So by construction, it is normal that the most common baseline achieves a rather good blue 1, but quickly collapses when N grows bigger. I wanted to show you an example of the generated last jobs. So in this example, the reference is a user whose last job was to be an e-commerce consultant working on profitability and notoriety issues. What's interesting to note is that even though all models seem to get stuck in the generation loop quite quickly, fastText CV-oriented expresses the communication aspects where the other models see a client relationship management, which is close, but not the same. However, the main point of this example is that the 3 models do express the marketing aspects of the job, which means that they could all somehow capture the essence of the career evolution of the user, since all models only had access to the person's previous job. Let us now conclude this presentation. We present Resume, a novel, self-supervised, free text-based approach to learn professional profiles that is robust to noisy text input and provides some insight towards explainability of the profiles through various evaluation tasks. This work is preliminary to numerous future work. In particular, we started exploring strategies to represent even more complex entities, such as companies and/or departments, namely with the goal of comparing those entities and extract meaningful relationships between them. For instance, we would love to be able to say that to extract from the representation of Microsoft that it is a competitor of Apple. But we're also interested in capturing and predicting even more elaborate signals, such as fundraising, company expansions, and even technological migration. Thank you very much for your attention. I'll be happy to answer any question that you have.
Okay, thank you very much. So if anyone has question, just please, sorry. If anyone has any question, just unmute your mic and just start your question.
Hi, Alejandro.
Yes, yes,
Hi.
please.
This is Ivan again. Well, I have a question. Thank you, Clara, for your presentation. If I understood correctly, you address a couple of tasks which were the industry categorization and destruction of skills. That's right?
And I'm sorry, I didn't catch the last part.
Yeah, a couple of, you said, if I understood correctly, that you address a couple of tasks, which were industry categorization, or three. Industry categorization and destruction of skills. And you presented some results for both of them.
Yes,
if I'm not wrong, it seems that destruction of skills is more difficult than, easier than industry categorization, could be? According to your results.
Yes, yes, absolutely.
And what is your thought about this?
Well, you have to realize that industry classification is, well, it happens on the LinkedIn backend. It means that it is not user generated, it is LinkedIn generated. So it's somewhat more precise. However, in the skills prediction, there are a lot of skills that you find on basically every profile. Those are, for instance, management, communication. Microsoft Office also comes out a lot. And I think that's what explains the 4% difference in the results. At least when I looked at it, that's what came to mind.
I see. Okay, thanks.
You're welcome.
Okay, thank you. We have time for more questions. Anyone? Okay, I have one question. So in the paper, you say that wrong predictions sometimes make sense to a human reader.
Yes.
I don't think you mentioned this today in the presentation. Can you elaborate a little bit more, or if you have some example of how this can be exploited, like in a real application?
Yes, of course. So indeed, I was short on time, so I could not manage to show you what didn't work as expected. But it is true that in some generated text, while it is not, it's not proper natural language that is generated, there are still some keywords that to a human resource officer would make a lot of sense. Say if resume was to be used by national agencies for employment, it could give very good pointers to the state officers to maybe help direct the candidate toward formations that they could be interested in.
Okay, thank you. So I think we are done with the time. So thank you, Clara, for the presentation. So we are going to the third paper presented by Monica Landoni. It's a short paper, Say It with Emojis, Co-designing Relevance Cues for searching in the classroom.
Thank you.
So now we are watching your presentation.
Yes.
So you can start whenever you want.
Thank you very much. My name is Monica Landoni. I'm here at the Faculty of Informatics in the Università della Svizzera Italiana, USI, in beautiful Lugano, Switzerland. And I'm going to describe to you an exercise we did in collaborative design with and for children in order to use visual cues to help them find relevant documents when searching in the classroom. The work was done with my wonderful colleagues, Muhammad Alian Nejadi from the University of Amsterdam, Theo Hybers from the University of Twente, Emiliana Murgia from Bicocca, Università Statale di Milano, and Sole Pera from Boise State University. So the motivation behind our study is very simple. Maybe you remember yesterday one of the speakers mentioned how adult searchers just stop at the first few results in a SERP. Clearly, children tend to explore linearly search engine result pages, and they stop very high up. And often the first results are not the most relevant for them. Also, our search engine result pages are not often optimized for children to use and can be confusing because they provide a lot of textual elements that for children can be a little bit difficult to make sense of. From literature, we also know that children tend to follow visual clues. They pay attention to highlighted terms, to thumbnails, and so something like that could be a way to help them find relevant documents. And we also know that children are very familiar with emoji because they use their smartphones for everything nowadays. So the intuition behind our experiment is that emoji could be the visual cues that can help children select better resources in SERP. The research question is kind of ambitious, if you like. Can emoji guide the information-seeking process of children when children are searching for educational purposes in the classroom context? It's very important for us to define the context, the age, and the kind of tasks these children are performing. But first, we need to explore via a collaborative design exercise what are the most intuitive emoji for children to follow and what constitutes for them a better emoji, so that something that helps them even better to find what they're looking for, to conduct successful searches in the classroom. And who could help us better than children themselves? So here I'm describing to you something that is very normal in the community, also part of the child-computer interaction community, a collaborative design exercise with children, in this case, children from primary 5 in Italy, that means aged 10 to 11. These children, this classroom is particularly experienced in using search tools because their teachers have really paid a lot of attention to that. And we're already part of some of our previous co-design studies on different topics. The search tasks we engaged them with were in line with curriculum and were also discussed with educators that helped us also to label the results in terms of relevant or not for our mockups. We generated using the Bing API safe search enabled 3 different SERP, and we use those to trigger and engage our children. Remember, this is not an evaluation. This is a collaborative design exercise. So we don't want to, to judge the best interface. We want to trigger children with those interfaces to come up with ideas for better interfaces for them to use. Also, in our previous studies and through the literature, we could see how relevant and useful in the classroom overlap. So they were deemed to be equivalent, at least in the context of this study. Because of the COVID-19 emergency, this study took place completely online. And this was a challenge, but actually was kind of interesting too. Those are, if you can see, the three mockups. We just use them to trigger discussion, to engage the children, to make them think out of the box. So we went for something very popular, the thumbs up and down, because, as we said, our children are very smart using smartphones. We really wanted something fun, so we went for rainbow and poo, and one of our authors really wanted to have a paper with poo in it, so here it goes. And then we went with something very classic, that was the traffic light metaphor. So we showed the same SERP tagged with these different icons, with these different emoji, to our co-designer children. And we also used, to stimulate their feedback, a revised version of the walkthrough material, a heuristic tool for early evaluation, where we asked children to tell us which of the three they prefer when looking for information about tornado. It was the topic in hand. Which of the three the classmates would use for searching for tornadoes, which of the three they would use for another search, and which of the three their friends, their peers would use for another search. Plus, we encourage any type of comments and feedback and to express preferences from them. And we also ask them to fill a simplified short version of the user experience question, or the standard one, just to get some feeling of how things were, just to make them elicit some more information. Anytime you run a co-design exercise, it's very important to define a protocol. Ours is divided into 3 phases, and we had a wonderful researcher in the field that was online with the children all the time. So initially she presented the 3 mockups, and were presenting results for the same query. Children knew, and they were often repeated, they were the experts, and we wanted their opinion on this. And we asked them how useful these mockups were according to their own point of view when considering peers, other children in similar situation. Then the researcher became a facilitator and asked children about their preferences, why they liked one more than another, and their comments and opinions. Finally, in phase 3, we thought the children had already been encouraged and stimulated, so they could assume the role of creative designers and were asked to produce sketches of new interfaces and icons that they thought were better suitable for the purpose of the emoji we introduced them with. So we wanted them to come up with their own design for other children to use. From the analysis, we got some emerging concepts. Well, as I said, this is not an evaluation. There is not a mockup that is better than another. This was not the case. But what was important for us was the discussion, was the consideration children came up with. So the first mockup, the one with the thumbs up and down, was judged clear and easy to use, but, and even we had a comment like Hans every day, but children commented on how difficult it was to see the difference between the thumbs up and down when you were scrolling fast, something we didn't consider. So from there, we took the concept of something that has to be easy to recognize on the move, because children are quick in moving around in a page, in a cell. The mockup 2 was the fun one, and in fact, everybody loved it and thought it was really funny, but was deemed not to be suitable to be used in the class. And in fact, one of the children said, "What do you think my teacher would think of it?" So it's very important to keep in mind the context of use of these icons. Mockup 3, the traditional traffic light, was considered easy and simple to use, but few children, very few I have to say, commented on how hard it was for colorblind people to make the difference between the green and the red. So inclusiveness came out as a desirable feature for the new icons. When we looked into what this means for future design, well, in phase 3, as you remember, the children were unleashed and they can act as designers. So they started sketching and drawing, and they sent us many interesting artifacts. So some of the children just went around on the web and looked for more traditional emoji that could at the same time be inclusive, simple to use, and not ambiguous, and suitable for the classroom. So the one you see on the left, the cross and tick, happy and sad, and angel and devil, belong to this category of existing emoji that respond to their needs. And this came out from the children, not from us, clearly. Some other children were a little bit more creative, if you like, and wanted to do something special, something different. So 2 children in different groups came up with the idea of the light up bulb and the switched off bulb as a way to clearly tag a result that will enlighten you, and one that is not going to be of any use, so to be left on the side. And one child came up with one icon only, not the binary metaphor we had in mind, but just one icon. This little, maybe you can see it's an arrow pointing up, because she assumed that all the results provided by the search engine would be good, would be relevant and useful, but only some would be suitable for children in terms of readability, in terms of comprehension, in terms of answering the question the child had in mind in a school context. So we even had this interesting insight outside the binary metaphor we had in mind. So what is going to happen now? Well, we think, we consider the use of emoji as cues for relevance. We treated children as experts that is normal procedure in different communities, like the one I'm part of, the child computer interaction community. And so we gathered a lot of opinions and requirements. So we treated them as experts and we engaged them in a walkthrough kind of heuristic approach to evaluation. The point was not evaluation, the point was to trigger a lot of creativity and get a lot of ideas on how to start this design exercise. We also kept the classroom context as dominant, so children were engaged while being part of the classroom and through their teacher. That's very important too. We saw how children actually liked the idea of using emoji, so it's a good direction to pursue. We also noticed how children are kind of formal, and if something has to be used at school, it has to be serious and doesn't need to be fun, even if fun is nice and pleasurable. And also, familiarity was not the driving force. Most of the emoji we presented were very familiar to them, but they actually commented more on inclusiveness and easy to spot. So this idea of being able to recognize a relevant and not relevant, useful, not useful result while scrolling fast was really interesting for us. Next step. Well, first of all, further exploration of other elements of the snippet that we can use, colors or the tone of presenting it, a multimodal way to present elements in the SERP. We also already elaborated on the metaphors the children suggested to us in order to extract their interpretation of relevance, so that we can do an interesting study of what relevance is for children, the many shades of relevance for children in the classroom, of course. We also want to explore an issue linked to the different levels of expertise that children can have with SERP. And in fact, as I told you in the beginning, we selected our co-designers as experts because they had been exposed to search online extensively by a very skilled teacher. Now, this could be a bias, of course. This is a bias, of course. That's why we call them experts. We want to see how children that don't have the same background would react to some of the design proposed by our co-designers. And what we are already doing is to compare search success with traditional and enhanced interfaces. So plain GUI versus our interfaces enriched with the icons. And I'm almost done. I need to thank very much our co-designers from Primary 5, Section C, Scuola Baccone, Milan, and their wonderful teacher and parents. Lorenzo, Giacomo, and Emanuela for the early feedback, and the student that did the mock-ups, Mikhail Kichev. And I'm done. Thank you very much.
Okay, thank you. Thank you for finishing on time. So if any of you has some questions, have some minutes for that. No?
Hi.
Yes.
Oops.
I have a practical question. Thank you very much, first of all, for this very interesting study. I guess this is quite fun to do that kind of studies. I would like to know what type of constraint you had with the parents. I mean, did they agree that you work on that? Because most of the time the parents are just, when you ask them, because we have to ask them, and when you ask them, they are aware of it's probably very dangerous to do such kind of thing, while they have not this on the usual days.
I completely agree. We need to ask as well. We need parental consent, and that's very painful. But we are very lucky because we run this exercise as part of the school day, as part of the school curriculum. Because as I told you, these children have been studying how to search online, and they're very profitable in that. So we got the consent through the teacher, through the school, and that makes life much easier. Believe me. If the exercise is seen as part of the educational curriculum, parents are much more willing to consent to that. Yes, but I agree, it's a big issue.
Many thanks.
Okay, thank you. Any other question? Yes, Ivan, please.
Okay, thank you. Thank you, Monica, for your presentation. Did you consider the possibility of having different interfaces depending on the information retrieval task? Not the same looking for a specific document or just an exploratory seek task?
Absolutely, we are exploring all these issues. That's a very good question, really. And we did a little bit of this, looking into emotional searches. We noticed that somehow, if the query children were posing had some strong emotion in it, positive and negative, children would be more enthusiastic about searching in order to solve the problem. And so we thought that perhaps SERP should also have some emotional dimension. But you're right, in terms of supporting browsing and searching, we should look into different type of SERP. We should also look into different type of ways to present information according to the child personality and the need, the task at hand from the teacher point of view. But yes, it's a very good question.
Thank you. It's a very interesting work. Thanks.
So actually, I have a comment because yesterday there was a presentation. Also, I think it was Sole Pera's work, where they did some work on emotions in snippets. So do you think there is some kind of connection with this? Like, at least with one of your future works about different interpretations of relevance, right? At least based on that, like you can suggest different sets of emojis or even the interface.
Absolutely, Alejandro, you are perfect. This is the perfect question. Sole and I are working together, and we will present at UMAP next week some kind of analysis we did of emotionally charged SERP and emotionally charged queries for children. And well, actually Sole spotted a nice Sigayal paper, a short paper last year by Gabriella Cazzai et al., where they were looking into how adults would be attracted by results with a positive emotion in them. And we thought, well, children would do the same. And we started looking into that, and we noticed how children not only are attracted by positive titles, but they're also attracted by negative titles, because emotions are running wild when you are a child. And so we did a little study in there. But that's a very interesting topic we want to do more, also in terms of redesigning the SERP and interpreting relevance. But thank you, it's a perfect question.
Okay, thank you very much. We're running out of time for at least about this paper. So we're moving to the next paper, which lucky for us is the same presenter. So it's an extended abstract called We've Only Just Begun, Children Searching in the Classroom, about this very exciting topic. So please, whenever you want, you can start.
Thank you. Can you see my slide now?
Yes.
Yeah, fantastic. I'm so happy. So this is my favorite. This is an extended abstract. and we used it as a perfect occasion to introduce ourselves to this community that we like very much. Again, I'm Monica Landoni from Emiliana Murgia, I can tell you a bit more, is our teacher and expert in education from Bicocca, and she is the one that makes sure that everything we do is absolutely ethical for children, but also appropriate for their age. Theo Hybers is not only a professor from the University of Twente, he lives in beautiful Hilversum and is the guy behind one of the founder of Wise Knows, and was part of both the soul and mind of our PAPI-IR project, where everything started from. And Sol, of course, is our wonderful expert in recommendation system. So without any further ado, this is a journey, and so this is why we have this postcard presentation. A journey in what we like to do and why we are doing it. So again, we mostly 3 out of 4 come from the IR community somehow, or more from the interactive and HCI part, but Theo and Sole are IR guys, where mostly we focus on adult users. And as Josiane is saying, it is not easy to involve children. But even when you do, there are some limitations. So when we look into how children use IR systems, we have somebody coming from the HCI community with their lens looking into interfaces, and the IR community looking into the algorithmic part. And mostly we focus on problems in query formulation and the behavior in information seeking. So we know that when it comes to children, again, you find small studies, and it's very difficult to replicate, as you saw before, any of those. Databases are not available because datasets are not available because of consent forms, privacy protection, and so on. So PAPI-IR, as the project I mentioned, was the one that triggered our interest, happened in 2009, 2012. It was an EU project where a bunch of academics, mostly, plus Atos, were looking into how to produce services specifically for children, for helping them to search for information. And we were looking into non-formal context, library, hospital, museums. So that triggered our interest. In our journey, we have a map. Every time you travel, you should have a map. A map that gives us the perspective, that is that of the teacher and the children, a place where we start from, the classroom, very important for us, the context, a name that is provides support to children, teachers, and learners. And what we want to achieve is to develop a nice evaluation framework for being able to compare our effort with those of other groups. Our children come and speak different languages, at least Italian and English. They come from different technical skills. Some of them are really techie savvy, some are not. And they have different search literacy because of the way the curriculum is managed in different countries. Plus, they are influenced or affected by other stakeholders, like their siblings, their parents, other teachers. So we need to take all of this into account. And we have to thank again our artist, official artist is Mice Hybers, for this beautiful map. So we started the journey, and you can see the stamp on the right. Here in Lugano at CLE 2019 with Sonny Cerca, there was a study into the design of a vocal assistant to search a school. And there we focus on the 4 pillars of our framework. There were the kind of user, children, the task, search for a school, the setting, school, classroom, the strategy, GUI versus vocal assistant. We also, the same year, went to Rexis and shared with them some of our concerns in terms of the many layers of complexity, but working with children, how we could build a little recommender system for children made by children, and what is the problem of scaffolding children properly in the school setting when searching for information. So then we managed to move on to a more teacher kind of environment, because remember, we have one of the four of us is an educator, a teacher, and so we wrote about what is the role of a teacher in all of this, and how the teacher can interact with IR system in order to make it easier for children to use them without the system being disruptive. Oh, why I'm not going? Oh, I cannot. What is happening? Oh, yes. So what happened also over the years in our journey, we keep meeting with a group of experts in child-computer interaction and recommendation system. The first time we met for this workshop was in Como in 2017, but then since 2018 we have met regularly. That is the major conference for child-computer interaction design. And there we looked into how IR system can be used for education, what is the concept of good, so what about relevance, and how different type of goods do exist, and also considering different dimensions, design, research, practice, and influence on policy. Our next steps are at the EE that was supposed to happen this year, but was moved to the next because of the COVID emergency, where we will talk again about teachers and what kind of requirements they have for using search engines in school, but also how we can help and how the curriculum needs to be expanded to include this type of literacy for children. Next week in UMAP, we will talk about the emotional and the sentiments in SERPs and how they have an impact on how children search, so that to help us devise the ideal search agent for them. And here you just heard what we did in terms of co-designing with children. It was an interesting, from our point of view, experience. So this is the end of our journey. We have embarked in a complex exploration, but we are very far from the destination. We've made a lot of stops and more will come, but the journey is more important than the arrival. And what is more important than anything are having good companions for your travel. So at the moment, we are really happy to be the four of us, and we have the skills of the luggage that is needed for this exploration. But in case any of you feels that they have a stop to highlight to us, a destination, or they want to jump in for a little while and travel with us, we are very open and very happy to have you on board. So I thought it was very quick, and it's even quicker than I thought. There we go. So I'm ready for your questions.
Okay, thank you very much. Yes, we have plenty of time for questions. I have a couple of questions myself, but let's see if anyone in the audience has some questions. So just start. No, anyone?
Yes.
Okay. Yes.
Okay.
Please.
Alejandro, thank you. Let me share my video. Okay, can you hear me and see me?
Yes.
Yes, I have a doubt about teachers. How do they teachers see this kind of tools to introduce search engines and these techniques into the classroom with children of ages between, I don't know, in this case, if you are talking about 6 to, well, I don't know, key 12, more or less, no?
Okay, it's true, you're right. We are talking about primary school, and for us, primary school is 6 to 10, 11.
Okay.
Okay, teachers come in all sorts of ways and shapes and forms, and some are very enthusiastic, some are very reluctant, some are not so positive. But I have to say that with the going online and being forced out of the classroom, as it happened in Italy and in Switzerland this spring, there is a very strong interest into anything that will make children experience better. So my experience has been very slow, in the beginning to convince teachers and head teachers, but I have a couple of private schools I worked over the years really well. And if they can see the advantage for the children, they would jump on it. And speaking about literacy, being able to use properly search engines is really important. So I think more and more it won't be as difficult as it was before, but I agree with you. Also, it helped if you provide some kind of service to them. Like we went into school from different exercise, and they can see a value out of it. So you need to invest, unfortunately.
Yeah, okay. But it is common to use this kind of tools in the classroom.
Yes, I was amazed because Emiliana, one of the authors, she is a primary school teacher, but she also has a fantastic label. She's a digital creative for her school. She's in charge of trying new technology for teaching, and she's also part of the educational department at the University of Bicocca. So she explores new venues and she tries things. And in a way, if you like, Fernando, it's like she gives the stamp of being suitable for the children, and the parents would go for her. And the same here. The small school I'm working with, it's easier. But even the public school is much larger and slower. I can see them changing a lot. So hopefully this will open. As long as we provide them with useful experiences, they will come on board.
Okay, thank you. Good luck.
Thank you.
Okay, thank you. Any other comments or ideas? Ivan has mentioned something in the chat. I don't know if you want to discuss about that. So he mentioned potential research lines, collaborative search, personality-based IR for children. So maybe, I don't know, if you want to discuss a little bit.
Absolutely. Yes. Yes, yes. I told you that we did this little exercise in recommending system by children for children, but we are very open to any. It's a very creative area of research.
Yeah, can imagine. I'm going to take advantage. I'm very curious about what about out of classroom. So I understand the context of classroom, but children are also doing homework, right? So, and they are probably also using a search engine at home for class-related tasks. So, is this something you are considering? Which would be the important differences, or I don't know?
This is absolutely part of our remit. When we say classroom, we also mean homework at home and doing searches at home. And what we notice is that simply by comparing the children where the teacher has been showing them how to assess the quality of sources, how to assess the language of a source, what kind of tools to use for search, are better prepared when they go home to use these tools. There is a paper, an oldish paper by Alison Druin in 2010, 2011, when she did study how children search at home, but not for school purposes, for leisure. And she could see different roles children can play, so 8 different roles. And there she could see the influence of siblings and parents on the way children would search. In our case, because we have this intuition, or we believe that the school has an important role to play. So if you have a father that works in IR, you're lucky. But if you don't, it could be really messy. Your first approach to search is going to be really complicated. So we feel that the school has a role to play, the teachers, willing or not willing, have to play a role in this, and a better prepared child can go home and do the homework and also search for leisure, but also search for parents and older siblings, because this is another issue. One of my students in Glasgow, she ran a study in school, but with older children, and many of them were searching for their parents were searching for information for their parents. So that's another interesting area. So searching by proxy, not only adult to child, but child to adult. So there is so much to explore, but slowly, step by step, we can get a lot of interesting outcomes from there.
Okay, perfect. Thank you. I think we can finish the session with this interesting discussion. So Josiane has some announcement to make. So please. Well, first, let me thank all the presenters of the session. Now, yes, Josiane, whenever you want. Josiane, we cannot hear you. Okay, but we cannot hear you. Yes.
Now?
Yes, now. Now we can hear you. Yes.
Sorry, because I'm handling too many things here. Sorry
Yeah,
about
no
that. So yes, just to say that tomorrow we start again at 9 a.m. So there will be 3 sessions. So 2 sessions in the morning, framework and system, and the other one semantic extraction. Then during the afternoon, we will have mentoring sessions where students will discuss with some mentors. So I really also want to thank the mentors who accepted to work with the student and to participate to this new type of face-to-face meeting. So that will be happen during the afternoon, and then there will be the closing session at 4 p.m. So we hope to see you tomorrow for the morning session, and also at 4 p.m. for the closing session. Thank you very much. I'm sorry for the mess.